And Nieto, you will do the introductions, please.
Okay. Hello, everyone, and welcome to the DIAS seminar. Today, we have as our speaker Devanshu Mukherjee from IIT Kanpur in India, and he's going to talk about from 2D droplets to 2D angles. So over to you, Devanshu.
Thank you.
Thank you, Neetu. So let me start off by thanking Professor O'Connor for the opportunity to present my work here, and also to Neetu, definitely, for coordinating this entire thing very nicely. So today I will be presenting a work which, in fact, was done in collaboration with Neetu. It came out around approximately a year back, maybe a couple of months here and there. It is done also in collaboration with Arghya Chattopadhyay, who is currently a postdoc at Mons, and Shubhankar Datta, who is a professor at, who was in fact my postdoc mentor at Nigeria. Okay, so sorry, yeah. So the interplay between unitary matrix quantum mechanics and 2D angles, this is quite well known and also pretty old. In fact, matrix models has been studied by statisticians for almost close to a century, and it was brought into physics by Wigner and was further applied, and various powerful tools and techniques has been developed towards understanding, to have better understanding of non-perturbative aspects of gauge theories and things like this, which can be recast in the forms of matrix models. Now, the expression that you see here is a 2D angles partition function with a gauge group SUN defined on a Riemann surface sigma g with genus G. Now, here you can see R is the dimension. R is basically, so it's written as a sum over representation, but dimension R is the dimension of the representation. G is, as I just mentioned, is the genus of the Riemann surface. C2 is the quadratic Casimir of the corresponding representation, and this beta factor is a parameter in which I have sort of repackaged the temperature, the sort of the time, and also the area over which the area of the manifold over which we are evaluating. Now, if you see this connection which I just mentioned between unitary matrix quantum mechanics and 2D angles, I will in fact talk about two very specific examples, very famous and old examples, one by Minahan and Polychronakos, which goes back all the way to 93, where they essentially mapped every representation onto a quantum state which carries the energy C2 of R. This is in some sense you should be intuitively able to see, because if you try to just map this partition function as given here to the standard partition function that we generally write in statistical mechanics, you see that this is precisely what C2R is, precisely something that corresponds to area, and this factor in front, dimension R to the power 2 minus 2, something like the degeneracy, whereas beta is something like temperature. Now, these energy states, what Minahan and Polychronakos did was they studied this also further in the context of 2D string theory. And they map these states to these 2D string states, which wind around some kind of compactified spatial direction. So the spatial direction is compactified. And in such cases, in such closed bosonic string theories, this is how exactly the partition function comes out. And in the large n limit, what they showed is that the governing Hamiltonian in the large n limit of these string states are identical to what is known as the Das-Javicky Hamiltonian. I will come to what the Das-Javicky Hamiltonian is, but for now, this is just to motivate what is the connection, the interplay between unitary matrix quantum mechanics and 2D angles. The second example, which is also quite famous, that I'm going to talk about is this work by Gross-Matitze, where they studied QCD in 2D. So they essentially studied a QCD2 partition function in the large n limit, and the saddle point equations that they obtained in the large n limit, they interpreted them as Hamilton-Jacobi equation. And what they essentially showed was that the classical Hamiltonian that they derived also turned out to be same as the Das-Javicky Hamiltonian. So what is the goal of our work? So let me explain that. The central point of our work here is to take a bottom-up approach, in the sense that I'm going to start with a unitary matrix quantum mechanics, and I will give you a prescription, a very geometric approach to construct transition amplitude and all higher point amplitudes for a variety of 2D angles theories. So again, this word variety I have specifically emphasized. I will come later to what exactly I mean by a variety of 2D angles theories. The next thing that I'm going to do is I'm going to construct, I'm going to consider fluctuations around classical solutions of this unitary matrix quantum mechanics, but in phase space. So most of our game and the juice of this talk will be centered around how to get out maximum amount of information about these 2D angles theories from the phase space picture in the large environment. And what I'm going to essentially argue is that once I quantize these little fluctuations around my classical solution and build up a Fock space with these states, the Hilbert space that I'm constructing essentially knows at large N about all the higher point angles amplitude. And in fact, amplitudes of other variants of 2D angle series, which I was just referring to right now. In fact, so by variety, I can just say right away. What I mean by variety is these sort of q deformations of the angle series, which we can also construct using our programs. So, before we dive into the actual mathematics of exactly how the prescription works, let me just give you a brief schematic of how we are going to do the construction. So here is a flow chart where I have tried to sort of encapsulate what we are going to do. So we start with the unitary matrix quantum mechanics, and this is a fact that I'm going to take, and it's a pretty well-known fact that various phases of unitary matrix quantum mechanics can be characterized by these things called free Fermi droplets. So they are parameterized by essentially an upper and a lower Fermi surface. We are going to quantize these droplets, and what we are going to observe is that fluctuations over these droplets, these classical profiles, they satisfy a double copy of U1 Cash-Moody, abelian Cash-Moody algebra. We are going to construct a Hilbert space starting from these quantized states. And what we are going to see is that this Hilbert space admits what I'm going to call a Young diagram basis. The point of going and making this basis change is that precisely when this Hamiltonian that I'm going to find out, when I'm going to calculate the quantum Hamiltonian, when it acts on this space, this states, the Hilbert space states that I'm going to construct, it precisely gives you that C2R, the quadratic Casimir, which I pointed out was the energy. And I'm going to give a map from these states to various, so essentially the central upshot of all of this, till you can say half of the arc of this flow chart, is to essentially map the states that I'm going to create in the Hilbert space to various kind of geometries, 2D geometries that I get in phase space of this particular unitary matrix quantum mechanics. Now, we are going to construct some very specific states in these so-called factorized. So Hilbert's product space will in fact be factorized. You will see that nicely factorized into two sectors, plus and minus, two chiral sectors to be specific, and certain very specific states constructed within this Hilbert space effectively will capture various kind of transition amplitudes, the partition function, and in fact you will see that all other kind of generic higher point correlators can be constructed, because essentially what we will be constructing is the building blocks. After that, what you can do is you can perform surgeries to come up with more and more complicated geometries. So finally, you will see that so step 9 is sort of a reconciliation, because starting from step 4 all the way up to 8, we will be only following one of the Hilbert spaces, only one of the chiral sectors. But when you want to put together, because you need to consider propagators from the plus as well as the chiral as well as the anti-chiral sectors, when you combine the two, you will see that we are going to need something called a composite basis representation, which I'm going to talk about. And finally, I'm going to make a few comments about how one can further generalize this and get correlators of q-deformed angles also. Okay. So with that brief description of the algorithm, let me jump into exactly what we are trying to do here. So the first line that you see here, the partition function, this is basically a 0 plus 1 dimensional theory. So you have just time. This is just and U is a particular element chosen from an ensemble of unitary matrices. This is how the action looks like. So the first term is clearly the kinetic term, and the second term, which is purely the potential, we assume for simplicity that it's a polynomial. Now, this is again a fact that had been well established since the late 80s and was continued further in the 90s by Jevicki, Sakita, and subsequently by Das and Jevicki. They figured out a way of going to the Largen limit starting from these kind of theories and writing down what is known as this collective field theories. So what do? Essentially, these collective field theories are essentially they try to capture the essential dynamics of these matrix models in the Largen limit. So the effective Hamiltonian for the system in the Largen limit turns out to be of this form, where my dynamical variables are rho and pi. And this rho factor that you see here, this is precisely the eigenvalue density. And it's nothing but a sum over a normalized sum over delta function. Now, the equation of motion, that is Hamilton's equations that follows from the Hamiltonian, which the effective Hamiltonian, which I just showed in the Largen limit, are these two. So one thing is quite obvious. I
have a question. Sorry. Is that Hamiltonian bounded below?
No, this is a cubic
before. Yeah, it is a rho cube term. So I'm asking, and it's also linear term in rho. Is it bounded below? They make rho very large. What happens? It has negative and large. What happens?
So this is eigenvalue density. Rho will be always strictly be greater than 0 the way it is constructed.
So there's a modulus sign in rho, is it?
There is no modulus sign in rho. I mean, if you see, rho is the eigenvalue density.
That's okay. Right? If suppose I take this Hamiltonian 2 and I quantize it canonical, the standard rules, does it have is it energy bounded below? Otherwise, how will you quantize it?
Speaking,
rho is like a radial vector. Then the quantization is very complicated. I already for ordinary thing because of the boundedness below. Okay, or rho is like a scalar field, a scalar x coordinate in a Hamiltonian. Then the question is x bounded below? How do you quantize to?
So so the way the mapping is done is that the positions, the locations, the theta i's that you see of the eigenvalues in U are precisely the thing that gets mapped to rho.
So in two, what is the domain of rho and what is the range of rho?
So rho is something which will always be greater than 0.
Then so the quantization of 2
it's not bounded, if that is what you are asking. It won't be bounded.
If it is bounded, then what is the boundary condition at the origin? Like the radial vector in quantum mechanics. Otherwise, you can't quantize it. Half-line radial vector is not a priori well defined.
I think he's not going to quantize it, Bal. I think he's not going to quantize it. He's going to claim that this is the quantized version, that this is the effective Hamiltonian after quantization.
Then I ask you again, what is the operator rho? How is it defined on a Hilbert space? And likewise, how is pi defined? Is pi conjugate to rho?
Pi is not exactly conjugate to rho. This is some kind of auxiliary variable that I have defined. And what you are going to see is a better set of conjugate variables is this p plus and p minus.
So what is the algebraic relation between rho and pi?
They have some Poisson bracket relation.
What is it?
Which I'm forgetting right now.
So normally rho pi is a conjugate momentum, means if rho is bounded below, it is not defined because it translates you out of the domain, out of the range.
Right, I understand. Yeah, I'm sorry, I do not have an immediate answer to this, but Yeah.
Okay, it's okay.
I have to think a bit more.
Okay.
So to reiterate again, this is not yet everything as of now is classical. I have not yet invoked any kind of quantization.
Perhaps it would be helpful just to say a couple of more words on the relation between Z and H. Where does that come from? What is meant to be the? You have written something that looks like a Hamiltonian,
right?
In
so
in terms of
U,
U,
collective field, right? So to go to the collective field way, so what you do is, you know for a fact that the eigen values of U can be written in the form e to the power I theta I. So you simply replace, you recast this entire object in terms of theta I. Then
so you
essentially
you diagonalize
exactly
U,
you diagonalize this, you write everything
and
in terms of theta I, then you take the large n limit.
Mm-hmm.
And the way that the large n limit is taken is this. This is how the theta is. And similarly, you know, the capital N basically scales to 1 and things like that.
Okay.
So everywhere you divide by n and you normalize things to 1. And finally, what you end up, if this is the identification, then this is what you end up as the Hamilton.
And you are going to claim that the saddle point equations capture the exact large n limit.
Yes, yes.
Okay. In the of the quantized version of the quantized model.
I have not yet. I'm going to quantize only fluctuations. I am not going to look at the quantization of this system.
Yes. Okay.
So, so what we get from these this particular Hamiltonian are these Hamilton's equation, and you can see there is an analogy with fluid dynamics where the first equation is essentially the continuity equation, and the second one is something akin to the Navier-Stokes equation. Where this particular variable dv is the flux of pi, essentially. And of course, this set of equation is very difficult to deal with because clearly they are coupled and they are non-linear. But what you can do is you can define two new variables, p plus and p minus, which are connected to rho and the derivative of pi in this manner. And what this does is that they decouple the two equations. It's still nonlinear, but at least they're decoupled. So we get rid of at least one order of complexity. Now, what we do is we look at the phase space. So in phase space, I go to this p theta plane. So p is basically my auxiliary variable, and I introduce a density function where, provided my p is bounded within this two sort of functions. So this is where I put my sort of boundary conditions, you can say, in my equations of motion. So provided my p is within p plus and p minus. So in this associated picture, this p plus t theta is precisely the profile of the upper Fermi surface, and p minus is precisely the profile of the lower Fermi surface. And as long as my p lies within, it gets support. And this is how rho is defined. It's essentially nothing but the integral of this density, and this flux of pi turns out to be the first moment of p. In some sense, this is what you would call the momentum. So these large n phases of this unitary matrix quantum mechanics correspond to and they correspond to various shape of these droplets. So these upper and lower Fermi surfaces are precisely what specifies the shape of these. And evolution of large n phases is essentially equivalent to how these 2D droplets evolve in my p theta space. Okay, so in terms of these p plus and p minus variables, this is how the phase space Hamiltonian looks like. Now remember that we are dealing with unitary matrix quantum mechanics. So there is a symmetry of U going to U dagger. What this symmetry essentially implies is that if you look at the area, which is the total phase space, that happens to be a constant of motion. In a sense, this is nothing but, you can say, in our current context, I am just simply stating Liouville's theorem. So what happens is essentially the shape of the droplet changes with time, keeping my area fixed. So this is the part. So as of now, as I was saying, till now, everything was classical. Now I choose a classical solution, a specific classical solution, and I introduce fluctuations over it.
Sorry, what did you mean by a symmetry of U goes to U dagger?
So U goes to U dagger. This is not, I should have written here. So these are generally symmetric polynomials in U and U dagger.
Oh, I see. I see.
I'm dealing only with Hermitian. I'm dealing only with. Yeah.
Okay, I see. You can. It's. I see. It's. Yeah, I see. You can replace U and U with U dagger, and the thing is invariant. Okay.
One small example is the standard Gauss-Witten-Wadia model.
Yeah. Okay, I understand.
And all I'm saying is. So that implies this. That's all is the statement. Okay. So what do I, so before I delve into it, what do I mean by quantization? So by that, I have to regularize the total number of states in phase space. So I divide my phase space into unit cells, each of volume h cut. And this is how I define my quantization. And the classical limit is essentially n going to infinity and h cut going to 0, such that hn is equal to 1. Okay. Now, if we want to define now the central thing that we want is we want Hamilton's equation, which is precisely this, the equation marked in 10. We want this equation to be exactly identical to the equations that we just derived for P plus and P minus, the upper and lower Fermi surface. We want these two equations to match. So we ask the question, what is the right symplectic structure that, or rather the right Poisson bracket that we need to define between the P plus and the P minus modes, such that equation 10 is essentially nothing but a rehashing of Hamilton's equation. So this is the Poisson bracket structure that we need. So P plus gives you a derivative of delta function. P minus Poisson bracket gives you a derivative of delta function, but with a negative sign. And P plus and P minus do not couple. They are simply decoupled. Now consider fluctuations around any specific classical solution.
Can I see the, sorry. Can you see the previous equation, please?
Yes.
Is P plus self-adjoint or no? What is a star actually on P plus or P minus? What is P plus star? P plus dagger?
Yes. I understand. Yeah.
Now, then if I multiply this by some test function in theta and integrate both of them on the left-hand side, it looks to me that you should get a positive answer if I multiply both by the same test function. But the left-hand side will be negative. So I'm a bit confused by this equation. Am I clear? Because multiply by f of theta, integrate.
Yes. I understand. You are saying with a shifting of derivative.
Because of the derivative of delta function.
Yes. It's derivative of, which is inherently an antisymmetric object.
Now, it is also not positive definite distribution. Delta prime is not a positive distribution.
Yes. Indeed. But the point is that you will see that you see the equations that I have written here, equation 5. So if you consider even for a constant potential, so consider the simplest case, W prime is equal to 0. Equation 5 is essentially nothing but the KdV equation. And what I have here in this Poisson bracket with these signs, etc., are nothing but the first KdV constraint, which essentially tells you that these things are integrable, etc. So, this Poisson bracket structure for the KdV equation is pretty standard. So that's my only defense you can say that I have for making this particular.
Okay, go on.
Okay, so if we consider fluctuations around these classical solutions, so the fluctuations come at order h cut, and these fluctuations now satisfy an equation like this. So And this particular equation that you see, you can easily also derive the governing Hamiltonian for the fluctuations, which now involves a p cube part, a cubic part, and as well a quadratic part. So starting from now, I am going to do one small simplification, which is that I am going to choose a very simple classical solution, which is that my w theta is a constant. And however, this entire analysis that you see and all the arguments that I'm making also goes through for some, also goes through for any other classical solution. So this is precisely the classical solution that I was speaking about, where since because these p's are constant and I restrict them to be plus half and minus half, so that this entire area is normalized to unity. Now, the fluctuations you can see from the perturbed Hamiltonian and the perturbed equations motion of p tilde, that again a very similar analysis tells you that this will be in fact Hamilton's equation, provided I impose this particular this particular symplectic structure between the modes. Not the modes, rather the fluctuations, p tilde plus p tilde plus and p tilde, which is very much similar to the classical case, except for this factor of h. But in any case, this is factor of h cut is going to go away, because this is the point where we are going to canonically quantize the fluctuation. So again, to reiterate, I had a classical solution. Now I'm fluctuating and I'm quantizing only the fluctuations. This is the picture where we are right now. So the canonically quantizing the fluctuations get rid of that factor of h part, and what we can do is we can easily decompose the p tilde plus and p tilde minus into its corresponding Fourier modes. And what you see is that these Fourier modes, they satisfy a abelian Cash-Moody algebra, which is what I also mentioned earlier at the beginning of my talk. And the area preserving condition, which essentially is the statement that u going to u dagger is the symmetry of my action, that essentially leads us to, that essentially leads us to the equality between the zero modes, excuse me, to the zero modes of p tilde plus, the plus and the minus sector. The entire point of going through all of these jugglery and telling you in details about all of this is to essentially convince you to the fact that even whatever potential you would have started with, however complicated or however easy, this sort of appearance of abelian Cash-Moody algebra as the governing algebra of the modes of the quantized fluctuations around a classical solution seems to be very universal. So because of the nature of our theory, our Hamiltonian breaks into two chiral sectors. So each sector being governed by the an or the bn operator.
Sorry, when you say abelian Cash-Moody, do you mean the conformal, something that's equivalent to a conformal field of a scalar field, the derivative, first derivative of a scalar field?
You can map this entire system. You can map this entire system to a p boson on a cylinder.
So
p plus.
I can map the entire system. Your mic faded there for a second. What?
Am I audible now?
Yeah, no. But you can map it into
a free boson on a cylinder.
Yes, right.
Yeah, where your p plus will turn out to be essentially like your current, a primary of weight 1, and you know, all of these things such as Sugawara, etc., all of them will actually go through for this. And,
okay.
Indeed, you so when I say abelian, by abelian I simply mean, so in general, a Cash-Moody would have also had currents appearing on the right hand side, but multiplied with a structure constant FABC, right? So that FABC is a 0. That's all I mean by abelian Cash-Moody. Okay. So what we just saw right now is that the abelian break, the Hamiltonian breaks into two chiral sectors, the plus and the minus sector, governed independently. And in terms of these an and bn modes, this is how the Hamiltonian looks like. With you can understand that the first line is essentially the harmonic oscillator piece, and the second term is a 3-point interaction piece, which is a very interesting, which is the interesting part in the Hamiltonian. And after some algebra, what you can do is you can find out what is the t dependencies of these operators E and E. And after some algebra, you can write everything in terms of these A and B operators defined at time equal to 0. And this is how it looks like. So you have a bunch of stuff coming from the 0 modes. You have this free part, and you have this 3-point interaction part. This is, in fact, I mean, I have written here that this is similar to the Hamiltonian obtained by Minahan and Polychronakos, but I should reiterate again that this is not simply similar. This is, in fact, identical to the Hamiltonian. And in the context of these 2D closed bosonic string theory, what they showed was that you can interpret this term, the last term, the 3-point dagger AA term, as the splitting joining interaction of closed bosonic string. So this is precisely in the context of string theory, will give you diagrams such as bands, you know, a string coming and a closed string coming and dividing into 2 more closed strings, and maybe the opposite process, 2 closed string coming and fusing into 1 single closed string. So yeah, these are the 2 sectors governing A and B. Now, A0 and B0, these commutes with all the ANs and BNs, and the Hilbert space now can be defined as.
Can I just clarify one point?
Yes.
The dependence on your original potential has completely disappeared on W.
Yes, it's not disappeared. What I am saying is I am doing my quantization around a classical solution.
Yes.
And all of this is around, I mean, thinking of H-cut order fluctuations around a classical solution.
And where is the classical solution? Where is the residue of the classical solution in your Hamiltonian?
There is no residue of the classical solution, because what I am looking at here is the Hamiltonian which governs the fluctuation.
But I would have expected the fluctuations to be sensitive to what they were fluctuating around.
Yeah. So no, I have chosen this specific case.
Oh, you said, yes, sorry, you've just chosen this specific. Okay, sorry.
Case of Asaf and Maya.
Yes. Okay, fine. Sorry.
I am doing it for this particular case, but my point is that this similar algorithm will also work for other classicals.
Yes. Okay.
But this is, you are right. Of course, here you can see the signature. Yes. The leading order solution. I mean, this is for computational simplicity.
Excuse me, I want to ask again. I'm sorry to keep bugging you, but that equation 20, where is that equation 20? My point again comes back because your terms like last term in H-int, it is an A dagger, A and an A. But there are, I suppose, harmonic oscillator states. Okay? So there are definitely states whose expectation value, for which this expectation value is negative. And there are also A0 terms, which has the same property. So I'm a bit not. So my question again is, why is 20 positive definite? Or is it bounded below?
So what I'm going to do is okay. So the best way to, so once I construct my Hilbert space, I'm going to act H on these states, and I will show you that this will be positive definite. It will always turn out to be the quadratic Casimir.
Okay.
So I will in fact prove that. Okay. I will demonstrate that.
That will be nice.
So because the quadratic Casimir associated with this representation is always positive definite. So that's it.
Okay.
So as I was saying, so now we start our construction of the Hilbert space, and we can in fact label it with a 1-parameter family of ground state, because my A0 and B0 modes were commuting with everything else, and this is how I define my vacuum. So this is how I so this is the definition of my vacuum, where all higher n greater than 0 things annihilates my vacuum, and my 0 mode basically gives me S as eigenvalue. So a generic excitation about the ground state would be essentially a bunch of A daggers and B daggers hitting on this S. And this will be a state in this tensor product Hilbert space. So these vectors that you see here, K, so this K vector is actually all the numbers. So Kn is the number of A dagger ends that is operating on S. So K is essentially the set of all these Kns, and L is essentially the set of all these Ls. And they parameterize excitations in the upper Fermi surface corresponding to P plus, and the lower Fermi surface corresponding to P minus. And as you just saw, since they divide it nicely into, and the factorize nicely into 2 chiral sectors, the two Hamiltonians H plus and H minus will independently govern the evolution of each of these Hilbert spaces. So I'm going to focus only on a single Hilbert space. The construction of H minus is identical. Okay. So first I'm going to start out with these states that I just defined, which is formed by a bunch of A daggers and P daggers acting on it. So what you see is that this follows a completeness relation with this particular normalization of ZK. Now, the catch here is that you saw this full Hamiltonian, right? This K happens to be an eigenstate only of the free Hamiltonian, as one would expect, because you saw that the free Hamiltonian is something like a harmonic oscillator, and what I essentially have here is nothing but those creation operators hitting on my vacuum. So what you expect is only to be a eigenstate of the free Hamiltonian, but not of the interacting Hamiltonian, the 3A term, which Bala was pointing out. Now, however, what this interaction part does is, I should still point out, the action of this interaction part is it keeps my level fixed. So something has to be kept fixed, and what this does is that this interaction part, when it acts on these K states, it makes sure that my level is fixed. Now, the expectation value of this P plus operator, and recall what exactly was P plus. P plus was precisely the profile of my upper Fermi surface. Now, that in this K state, which is the so-called ripples, that precisely follows this sort of a relation. Notice here, so you have this classical piece and you have this deformation coming with a H cut. So these K states that that I just described, you can think of them as quantum excitations over the ground state. So these are the ripples on the upper Fermi surface. Of course, correspondingly, you will also have an expectation value of P minus, which will give you ripples on the lower Fermi surface. Okay. Now I'm going to talk about some very specific states, namely the coherent states. So this is how I define a particular.
Where did you make the transition to fermions here? Because you're talking about a Fermi surface.
Yes. So there is, I should have probably mentioned this. So there is a very nice equivalence by which one can think of these kind of unitary matrix models as a model of free fermions lying on a circle, but restricted with this potential W of U. That you can see very easily because you see the measure that is here, du, is essentially but nothing but like a Haar measure. So if you write it in terms of your eigenvalues, du, when you write down the
eigenvalue proportion, yeah.
Mm-hmm. Yeah, you will get a log potential, right? And precisely when all the eigenvalues they try to sit on each other, there is a repulsive force. In this sense, this is a fermionic model. Because in some sense you have this Pauli exclusion principle. So in this sense, this is a fermionic model.
But do you have a map to fermions here?
Okay, the map to fermions is pretty well known, and it's there is a concrete map. Yes.
Okay, but you're not going to use it.
Yeah, I'm not going to display it. I am going to use it. I will. All the formulas and everything that has gone into will not be explicit. So coming back here, this is how I define a generic coherent state, where these tau n plus are nothing but some arbitrary parameters that are going into describing the coherent state. Now, if you look at the expectation value of this P plus operator in this coherent state that I just defined, what you see is you get an expression of the form 25. Now look at what happens because of this factor of H cut in this coherent state that we defined. Equation 25 gets this piece which is something like an order 1 deformation. So recall that we defined ripples which were proportional to H cut, which came just by acting, which were essentially these K states. Now these coherent states that we defined, they essentially capture these sort of finite size deformation to an already classical solution. However, what you can show that the dispersion, the quantum dispersion for these states tau plus with respect to the operator P plus, this in fact vanishes. So in this sense, you can call these states classical. So essentially, depending on the shape of this droplet, we have classified our Hilbert space into 3 categories. So the ground state, we have a classical droplet. The ripples are essentially given by these states K, which are found by hitting the vacuum with a bunch of A daggers and B daggers. And this coherent state, which I just showed here in 24, this you can think of as finite deformations of the classical droplet.
What happens if I take superpositions of coherent states? I can do that, no? So it's a quantum theory.
Yes, of course.
So what happens to the non-diagonal matrix elements?
So they will also come as a order one, as a order one deformation to the class. Yes. Yeah, you can also start with a superposition.
By order one, that's I don't follow. Why?
So by order one, I mean the quantization, the fluctuations, they come at a certain order, which is the order of H cut. This is how I'm parameterizing my fluctuations. If I calculate the expectation value of this P plus operator in this coherent state, this state 24 that I have defined, even if you take some linear combination, you will get some number like this, which does not contain any H cut sitting in front. Unlike, for example, the second term, which was precisely what we got as expectation value when we acted on with a state K, when we calculated expectation value with respect to state.
Okay.
So in this sense, you will get order one deformation means you will not have this factor of H.
Okay.
So this is the classification of the states. Now I'm now actually gradually going towards answering Bal's question, and this is the point where I'm going to answer it. So the biggest problem here is that you notice that this K is not an eigenstate of the interacting Hamiltonian. So we need to somehow a small thing. I just wanted to ask, how am I doing this time? Hello.
Yes. Yeah.
How am I doing with time? How long do I?
Yeah, we're okay. We're asking questions, and you don't need to worry too much about the time.
Okay. So please feel free to interrupt at any point and continue asking questions. Sorry, I should have mentioned this at the very beginning.
That's okay. I should have mentioned it earlier.
So, so as I was just saying, that K is not an eigenstate of the interacting Hamiltonian, and what we do is we define this following very specific class of states. So this is what we call the Young diagram basis. So what do I mean? So what we mean is, so given a representation of a Young diagram, given a partition, it always specifies a particular Young diagram, and with that I associate a state, and the way this state is constructed is basically as a sum over a linear superposition of the K states that I defined, but with certain very specific coefficients in front. This chi r plus k is nothing but the character of the conjugacy class of the permutation group Sk, and this Zk is the normalization factor, which is defined like this. What you see now is this R plus happens to be an eigenstate of the full Hamiltonian H plus, and this is an exact eigenstate of the full Hamiltonian. So you see, the problem was this K state that I defined only got me this part as the eigenstate. Now this R that I have defined actually is an eigenstate of this full object in a non-perturbative sense, including this 3-point function. And this eigenvalue, this E, the eigenvalue E in the Largian limit turns out to be exactly H cut square by 2 into C2R. Now this C2R is the quadratic Casimir associated to this representation R plus. So in this sense, this E is always positive, and this is in fact exactly the result, the interpretation of Minahan and Polychronakos, which is that this energy is precisely what can be mapped to the quadratic Casimir in the context of D angles also. So here, when I'm actually doing this calculation in 27, there is a lot of machinery which I have not explicitly put in, simply because they would take us in a bit of a tangential direction. But you see, here everything, these A and P, these are bosonic operators, because as you just saw, A and B follows a bosonic algebra. However, in order to actually perform this computation, so this is something that I am talking about, entirely from a point of view of, I would say, computational convenience. A much better thing and a smarter thing to do in this case is to use a standard trick called fermionization, or the other way to go is bosonization, which has been in the condensed matter literature for quite a while. And the way to do it is that you can define, starting with these fields, this P plus and P minus tilde, P plus tilde and P minus tilde. You can define certain operators from there. In fact, they look very much like vertex operators. And you can define certain fermionic objects using these P plus tilde and P minus tilde. And so if you mode expand these fermionic wave functions, you will get a fermionic algebra, a Grassmann-like algebra. And in such a case, calculating the action of H plus on C2 becomes much more easier, because whenever you have two fermions, they are always going to create a product, and it's going to annihilate the whatever is going to come. This is not a luxury which you have for the particular operators that I am working with here, because when you actually want to compute this, you actually need to painstakingly go through, you have to act your A all the way through K, essentially a normal operator for bosonic operators, which is significantly much more difficult, at least computationally. So instead of going into that details, I mean, I've just essentially stated the result that this is. So coherent state tau plus that you saw, this can be written in a basis of R plus. So we wrote it in the K basis, if you recall. This is how we wrote, as something that acts on the vacuum S. We can write it as a linear combination of R, and with a little bit of algebra, one can in fact evaluate these coefficients in terms of the eigenvalues of the matrices that they appear. So what this equation essentially gives us is a map between these infinite dimensional parameters, which quantifies and parameterizes my coherent states, and this set of angular variables theta1 to theta n, in the n going to infinity limit. These were precisely the eigenvalues that appeared in the matrix. Now, what you have is essentially using certain very nice mathematical identities. What you can show is that you can recast this object as nothing but the Schur polynomial associated with this vector tau plus. So recall that tau plus is a vector. In fact, it's a bunch of numbers. And so what this does is,
sorry, 29. Why does it converge the right hand side?
Sorry, why does?
You're summing over I.
Yes.
I suppose I goes for large n to infinity.
Yes, yes.
So why does it converge?
Yeah, I mean this kind of convergence issues are not exactly that we concern ourselves with, but
how do I take a step?
Sorry?
I mean, I suppose that this is a mapping from tau plus to some auxiliary Hilbert space given by tensor product of operators on a circle. So
yeah, so this
I need to give a Hilbert space. No, I need to give a scalar product to make sense. It's a quantum state.
Right.
What is it? What is it?
You can. Sorry. So the Hilbert space does have a well-defined inner product, etc. This particular expression that you see, 29, this essentially follows. I don't know if I have it here. This essentially follows from the expression of and the definition of the density that we defined here. Using these, one can define. But regarding the convergence of this particular series, sorry, I do not.
A similar question is, how does one know that tau plus, the eigenstates you are writing in 28, they span the full Hilbert space?
So, okay. No. These are specific coherent states. They will not span the full
They are
Hilbert space. They
eigenstates
are
of the
only the
Hamiltonian, no?
Yes.
But how does one know that you have captured all the
No. Tau pluses are not the eigenstates. R pluses are the eigenstates.
R plus, sorry.
Of the full Hamiltonian.
How does one know that
R plus outer product, R plus outer product is complete, and R plus prime inner product is also a delta function. So it's a very nice basis in that sense.
Does it span the full Hilbert space?
Yes. One can check using 26 and all the machinery that the definitions that I defined.
Okay.
Provided, of course, these numbers are very important. These characters and this ZK, you can show that this indeed is a complete basis, R plus.
Okay.
So this is indeed a very nice and kosher Hilbert space. Okay. So we have all the machinery ready, and now we can begin starting to write down our various observables and amplitudes for the 2D angles. Okay. So first, let us consider. If you recall, in the first slide, I showed a picture. I gave an expression of 2D angles on a closed Riemann surface with G genus. Now, first we start with the cylinder amplitude. So consider transition between two coherent states. One is defined, I'm calling tau A plus, another tau B plus. And the transition time is capital T. And if you calculate this, this is precisely what you get as the cylinder partition function for 2D angles. Now, this is, so of course, what this means is that these objects that you see here, tau A plus, the data that goes into parameterizing your coherent state are also the data that goes into writing down your holonomy. So there is a map in between these set of numbers tau A plus and the holonomy data that has been specified of the two boundaries. So in fact, this is precisely what are mapped to the droplet profiles plus and minus. Now, there is a special point in the tau plane, which I am going to call tau star, where all the parameters tau I plus, they are 1. Now, Schur polynomial for such a distribution becomes very trivial. They become exactly equal to the dimension of R plus. So that is essentially like taking this and choosing one of the holonomies to be trivial. So essentially, you are sort of closing down one of these circles, and what you are left with is simply a disk. Now, if you do this identification and if you choose trivial holonomies for both of these circles, you close off both of them, both of these ends, and what you end up is with a theory on a sphere. And this is precisely the disk amplitude, where you have, because I closed one of the circles, I chose one of the holonomies to be trivial, which in this case is tau A. I have replaced it with dimension of tau R plus. So choosing trivial holonomy is again, to reiterate, choosing all the tau I pluses to +1. And the sphere amplitude is precisely exactly this, which I advertised again in the very beginning of my talk. Although I did it for a generic G genus Riemann surface, so in this case G is 0. Otherwise, you would have the factor 2 minus G. And again, another important thing that you see here, that the C2R indeed can be interpreted as the energy, and this H cut T right now, which played the role of temperature. Now here essentially is the time over which this propagation is happening. Okay, so we have got all the building blocks: the disk amplitude, the sphere amplitude, and the cylinder amplitude. How can we possibly go ahead and define higher point functions? So now this is a part where I am going to make a bit of an ad hoc proposal. In the sense, by ad hoc, I mean, I really do not have, so let me start by making, by proposing the following definition, which I'm going to call a droplet operator. This is how I'm going to define my droplet operator. It is a sum over over outer product of R plus, but now weighted by this factor in front. And these are the main properties of this operator. So the thing is that for a mixed ensemble, for a mixed ensemble, what you do is you define a density matrix in this form. where this rho g plus is the density matrix, and PR plus are precisely the weight factors with which you are weighing all these R plus states. Now, this expression that you see in equation 35 for PR plus, this is something you can say is a bit mad, in the sense that I sort of wanted to reproduce my answers for a generic G-genus surface, and henceforth, looking back, I sort of reverse engineer and figured out this. So this was this is one thing that we are in fact currently thinking about, if there is any better explanation of proposing this kind of a weight factor when describing the density matrix for a generic ensemble. So the partition function for the chiral sector is simply the trace of this density matrix, which in fact nicely matches with.
Sorry, what is tau star in this that gave you the identity?
Tau star is a very special vector where all the coherent states the parameters are tuned to 1. So tau star basically means I'm writing a coherent state where all of these tau n's are plus. Tau n pluses are 1. Okay. All of them are 1. So it's just a n dagger by nh. So the reason for going to that very specific coherent state is that when you are sitting at that point, your Schur polynomial essentially boils down to simply the dimension. If you recall, my goal was to essentially get something like this. And the formula that I showed was for a closed Riemann surface. There were no operator insertions. It was a completely closed surface.
Yes. Okay.
Yeah. So here what you have, this endpoint means I'm actually making n punctures. There are n operator insertions, and at the same point of time, G is.
Yeah.
Is this visible? Equation 37?
Yes, no, yes, it's visible, yes.
So in fact, the formula that I have in 37 is a bit more general, in the sense that when I started off with the formula, I did not have n punctures. I was defining something on a generic. It was closed. Now here I have n punctures, and this is a generic endpoint correlator. So in a sense, you can think of 37 as the in our context the LSE formula.
And SR plus is the Schur polynomial.
Schur polynomials, precisely. And so this is the most generic thing that you can have. You have these n punctures, and around each of these punctures, you see these tau plus AIs. These specify your holonomy data. And this is how you calculate the endpoint correlator.
Okay. Yes. Okay. And the object that Bal was concerned about, the sum over the exponential of, is it e to the I k theta I, sum over I?
So Bal's
this expression here, these ones, I mean, if I had normalized by 1 over n, I would have got moments of the distribution. I think they would have been moments of the distribution, the kth moment. Is that what they are? Because the sum over I, the theta I are the thetas that you introduced earlier. They're the eigenvalues of the unitary matrix.
Right.
The holonomy, which are related to the holonomies.
Right.
So these ones would, that expression there has to be n times the moment of the density rho. And
yes.
And you're taking that to be t tau plus tau k plus.
Indeed. In fact, by the mapping that I defined, yes.
Yeah. Okay.
I don't know, but I think that what is involved in 29 is an infinite tensor product of Hilbert space on S1 on circle. Infinite tensor product, but knows that that object is.
I don't see any Hilbert space there at all, Bal. It just looks like it's a function.
Okay, but you need a scalar product. Otherwise, I don't know what physics is in 29. It's just a formula. So I need to take expectation values, which he does later on.
Yes, you would. You
So
should
what
take
is-
expectation values at some point. Yes.
So it is a Hilbert. Presumably, it is supposed to be something to do with the Hilbert space. Okay, but infinite tensor product of L2 of S1 without any further statement is known to be, let me say, highly vicious. Already
Yes.
one knows from
Yes,
Murray
absolutely.
von Neumann, old papers of Murray von Neumann, one knows that object nobody wants. Okay, it is really horrible because there is no topology. What do you take? What do you mean by it? Infinite tensor product? One doesn't know. Okay, so that is why I was puzzled. With 1 over n that you are telling, I don't have any problem. 1 over n, then it makes sense. It's L2 on this.
I think there's a 1 over n naturally
1 over
in
n
there.
squared that converges when you sum over n.
Yeah, if I do have a 1 over n, then yes.
It's 1 over n squared, you get zeta function thing, no? That converges.
Yes. Yeah.
I would have put a 1 over n there, but I'm not sure why whether you need it in your construction or not.
No, I understand the need of 1 over n. Just that, yeah, I have to go back and look at the computation.
I have another question related to
Yes.
Denjo. At tau star, the coherent state you are writing, is it well defined? Scalar product is well defined.
Well, if I had the 1 over n there at tau star, it would be 1.
Yeah. So you are taking exponential I n, coherent state is exponential I n dagger summation n acting on the vacuum, right?
Yes.
That object seems to have a divergent scalar product. I was trying to do it in my head, but I may be wrong. Without any Z. Normally you write Z A dagger. And Z is not allowed to become 1 all over the place. You know? You get the scalar product involves exponential minus mod Z squared, mode by mode. Okay. So if you take scale summation I Zi squared will converge if Zi is less than 1. But is it equal to 1? I don't know. I am not clear that that object is well defined. I don't know.
We checked all of these things, and I can assure you the states tau plus are well defined for all the tau n plus, and we did check all the inner products, etc.
Okay.
Here, I mean, I am being also a bit sloppy, but yeah, there are normalization factors, etc. also sitting in all states.
Okay.
So there are 1 by n factors which will follow from by imposing normalize like I'm going to demand that these states are normalized to unity.
Okay.
So those factors are there. I'm being a bit sloppy with it. So because I want to mostly just show the mathematical structure that I get and the physics statement that I get by doing this kind of a procedure.
Okay.
But I can assure you that all those at those special points also these states are well defined and the Hilbert space is. And as I just said, even H plus also acting appropriately on the R plus states, they will also give you something C2R, which is positive definite, and also H R plus R. I mean, the R plus base is indeed a good basis. It is complete, and the R plus and R plus prime indeed is a delta function. Okay. Now, I also promise that I'm going to make a few comments on certain variants of Yang-Mills theories. And the particular variant that I'm going to talk about is what is traditionally known as this q-deformed Yang-Mills theory. So the standard story is that when you have this sort of q-deformed Yang-Mills, this deformation parameter q is something that you introduce in the gauge group. So you have this, so take for example SU2Q. Essentially what it means is that instead of following the standard rules, your matrix elements of SU is not going to commute nicely, and it is going to have the non-commutativity is going to be sort of encapsulated in this parameter q. So in order to understand the transition amplitudes, etc. of theories like this, what we do is we do something slightly different. We keep working with the UN gauge group, but we define a very special class of coherent state. And this is how I define in equation 38. This q is the deformation parameter, such that q is bounded between 0 to 1, and this gamma that you see is q to the power capital N, N being the rank of the gauge. So in the limit of q going to 1, we indeed get back our the tau star state. And one can also further show that if I construct these inner product between the r plus state and this tau plus q that I have defined here, what I essentially get with is the q deformed dimension of r plus. So this object also has its own definition. So q deformation has a very standard definition, which I'm not explicitly writing here, but one can see that in the limit q goes to 1, it boils down to your usual. One can invert this formula also, and one can write down this t plus q in terms of this r plus basis and perform the same similar kind of computation that we saw for this non-q deformed theory right now. Further, if you consider q to be e to the power I gs, gs is something that you can retrospectively map to the string coupling, and you work in the double scaling limit. So by double scaling limit, okay, I should have written it down. What I mean by double scaling limit is essentially n going to large, gs going to small, such that n times gs is equal to lambda, which is the tooth coupling, which is the usual tooth coupling that we know of. This remains fixed. What you recover is the disk amplitude of q-deformed Yang-Mills theory in this limit, where there will be factors of gs here. There is a typo, and so where this gs can be mapped to h cut t, t being the time over of propagation. And in general, for arbitrary holonomies specified, which will now actually contain two data. It will contain the deformation, the q deformation parameter, as well as the data of the coherent states. You can also recover the disk, sphere, amplitude, or q deformed theory. So what is the advantage here? The central advantage is, generically in a q deformed theory, the standard lore is to deform the gauge group. Here, we essentially have recovered cylinder amplitude, sphere amplitude, and disk amplitude for a q-deformed Yang-Mills theory with our usual UN gauge group, which is computationally easier to work with, by simply bringing in this deformation parameter into my definition of this so-called quote-unquote nicely defined coherent states, whose transition amplitude precisely replicates my various observables in the 2D Yang-Mills. So this is essentially the main upshot of our map. So now, if you have noticed, one thing that I had been doing for a while now is I had been looking at only a single sector, which was the positive sector. Now, this also has a negative sector, and in order to get the full partition function of the full UN Yang-Mills theory, 2D Yang-Mills theory, what one needs to do is use both of these Hilbert spaces to construct the full Hilbert space. So this requires something called composite representations, which I am referring to here by this r plus r bar minus. So what exactly are composite representations? So here you see in this picture, r plus is a typical Young diagram corresponding to a representation. R minus is a typical Young diagram corresponding to a representation of a particular representation coming from the lower Fermi surface. The composite representation r plus r minus bar is essentially formed by doing something like this. So the negative one, you think of them as anti-boxes. So instead of placing Young diagram boxes along this direction from left to right, you start placing them from right to left, the largest one being at the bottom and slowly decreasing upward. The total length of this particular column must be capital N, which is the rank of the gauge group. And the composite representation is essentially obtained by filling up this and then finally removing the r minus bar sector. So what you have here is the composite representation coming from the two representation r plus and r minus. So another basis for the full Hilbert space, as you would have expected, is simply the tensor product of the two sectors of the r plus and r minus states that we constructed.
Hey,
and the two,
I mean, why is this a natural construction? It looks completely ad hoc to me, but
yeah,
presumably there's something.
Yeah. So the thing is that, so UN chiral theory is going from UN chiral theories to the full Hilbert space. It has been noticed that composite representations are simply the ones that actually works. The reason is because so there is something. So this has something to do with overcounting. In the sense that if you look at R plus, and if you simply write down the conjugate of R plus in the limit n going to infinity, it does not necessarily capture this particular representation, simply because you have infinitely many boxes that you can place along this column. So it has to do with subtleties when you take the n going to infinity limit. Hello?
Yes, I'm looking at it, but you have a very particular construction here where you took R plus and R minus, you reversed R minus, you then filled in something, but you deleted R minus.
Yes.
So it looks like
this is just the prescription of constructing this particular representation of R plus R1.
So I think that there's a complementary representation to R minus,
yes,
which is what has been it's been added to R plus.
Yes.
So maybe that's what's really going on here, that you have taken the complement of R minus and you have adjoined it to R plus. I'm not sure if they were.
Each young frame is associated to a UN representation. Okay?
Yes.
Right.
So what does this object belong to in terms of UN representations? Not n going to infinity. What is the UN representation which emerges from this this manipulation of permutation?
I mean, it is just called the composite representation. This is the very definition of it. What I was talking about, like what I was answering to Tenjo, was the reason why you do it. It is generally, so I'm again forgetting the argument, but what Gross and Matitsin, what they showed is during their analysis of QCD2, that if you naively group Young diagrams in terms of their total box number, then the U infinity representations, when this is a subtlety that happens only in n going to infinity limit, then it turns out that you somehow undercount all the possible U infinity representations. So I'm forgetting the exact argument, and the undercounting is exactly by a factor of half. So the reason to go to composite representations is in order to make sure that you have indeed counted all possible representations. This is a matter of counting the number of in the strict n going to infinity limit. That's the catch. This is the reason why you require this.
Yeah, in the large n, whenever you are writing a representation, you can always try to write the conjugate representation, and you can say that that representation is missing from the sum.
Yes.
And here exactly that's what we are doing. We are actually combining R plus and the conjugate representation. That is why this like R minus bar, it's not R plus and R minus.
Yes,
the red box here denotes the conjugate representation.
Yes,
that we are combining.
I mean, whatever you see here in red. Yeah. I mean, does that answer your question, Denju?
I think so.
I was thinking of Denjo. What is U infinity anyway?
It's some limit of UN, presumably. It's only defined as the limit.
How is the limit taken? I know that there are many limits.
Yeah, it's a particular limit.
Katz, the book by Katz and Ashok Raina discusses them. Okay, And also it depends on splitting of the Hilbert space into compact operators and all kinds of things. So there are many topologies in defining U infinity. What is this? Because that will answer Denjo's question of what does this composition mean intrinsically, without intrinsically means some rule with U infinity, which is uniform.
Yeah, see, for finite n, you do not have any problem. You would not require this, because it will also belong to this kind of object, will also belong to your R class, etc. You do not need to construct things with negative box number.
Raju, but you really haven't. It's not clear you have described anything with a negative box number, have you? Where's the negative box number entering here?
So the negative box number, so everything to the right of this line is positive box number, everything to the left of this line is negative box number.
Oh, you wanted to, yeah. But in the end, what you've done is you've taken a representation, as Nieto said, which was your R minus.
Yes, I have taken the conjugate of it. And
you
then
took the conjugate of R minus and you've placed R plus to the right of it.
Right.
But
and it joined it as boxes. Yes, Nito?
These two are just equivalent ways of writing the same representation.
The same.
These are not like, these are the same things.
What do you mean they're the same thing?
If you talk about UN representations and you draw Young diagrams corresponding to those, then you can have negative boxes in that.
But I don't see any negative boxes now. In the end result, Nieto, I don't see any negative boxes.
Yeah, so
I start counting from the left to the red.
Yeah, so there are two ways of talking about UN representation in terms of Young diagrams. One is that you can draw negative boxes. The another one is that you can write it as SUN times U1 mod Zn, and then then U1 just gives you a charge which will be just like, you will have some number which you can which you don't have to worry about when you're drawing the Young diagrams. It will be like just some factor. So you are in that way, when you are drawing the representations, you are essentially drawing SUN representations, and those will only have positive boxes. So those are two different ways of drawing UN representation, and these two representations here are the similar things. These are again UN representations, but drawn in two different ways.
Okay.
I don't know if that makes something clear.
To answer your question a bit more clearly, I mean, it's a rehashing of what Neetu just said. So when you have UN decomposes into SUN times a U1 by Zn.
Yes.
So this U1 part is parameterized by some particular parameter, Q, say. I can fine tune Q, and if you write down, say, for example, the quadratic Casimir or something like this, what you will see is that this quadratic Casimir can possibly become negative. So you want to avoid that problem. So what you do is, so this is the reason why box number can also become negative, because I can always dial that Q and make things go negative. And what you try to do is, you try to make sure that everything is written in terms of positive box numbers. And essentially, what this procedure does is, it tells you that this representation is effectively same as this.
I see. Okay.
This is the central state. And it has to do with the difference between the subtle difference between UN and SUN.
Okay.
Because what I showed you was actually the partition function of UN Young. So the central upshot is, so you have two possible bases. One is this direct product, another is this composite basis. And this is how the two bases are related. So this N, these are numbers. These are known as Littlewood-Richardson coefficients. They come up at various places in the context of representation theory. And so what I do is,
let me ask again, following Denjo. Is this tensor product commutative? If I write R tilde minus tensored with R plus, do I get the same answer?
Oh, this is,
Now, how is it defined anyway? R tilde minus, according to the roots you are given, is obtained, is a complex
I'm
conjugate.
sorry. There is a typo here. This should not be a bar.
Okay,
This is,
R minus,
this is R,
tensor
yeah.
R plus.
Yeah.
Equal to R plus tensor R minus. As representations, right?
Yes, yes.
No, it shouldn't be. I mean, if I did the construction with R minus, the top part here on the right would have an R minus set of boxes rather than an R plus set of boxes, and you'd have the complement of R plus, and they're not equal.
They are not equal, it seems to me.
Yeah.
So
Yeah,
this is the commutative tensor product.
It's a non-commutative tensor product, yes.
What is
I
it?
mean, as he has described it, if I'm understanding it correctly.
Yes. So is it even a representation?
Is it? Sorry, could you repeat?
Is it even a representation of UN? Does UN act on this tensor product?
Representation of UN.
How does UN act on this? Not infinite n, for finite n, how does it act? I think that from...
But these results are only true in the large n limit.
Yeah, this is the... I mean, for finite n, I don't know.
For finite n, all these things will not hold completely. It will break down.
For finite n,
the prescription will break down.
Okay.
I mean, asking finite n results from this. Yeah, it's not so straightforward how to get to finite n.
Okay.
Okay.
Can I just say one more thing? So for finite n, actually, you can check it explicitly if you write all the representations that this thing will not work out, because if you look at the center diagram, the condition is when you are drawing this, the number of boxes like in the center row, it has to be less than or equal to n. And if you explicitly write, say, SUN representations for some small n, then this will not work out.
Yes.
This condition will not hold.
Yes, that's clear. Yes.
Because you are talking about UN, so you can't have more than n rows. So each of these representation cannot have more than n by 2 rows, basically. So that's a restriction.
But this construction should work for smaller boxes and n large enough, or a small number of boxes and n large enough. It should make sense.
N has to be, yes, n has to be large.
And
so it's something I would say which will specifically work only in the double scaling.
Okay. Yeah.
That's my guess. Okay. So generic coherent state for a 2D droplet is simply the tensor product of states from the upper and lower Fermi surface, and this is how it is given. And what one can do is one can use this inversion formula, where the composite representation are written in terms of this tensor product decomposition. Sorry about the typo here. There will just be a R minus. One can use this inversion formula to in fact show that this H plus and H minus acting on this states which we defined in the composite representation indeed recovers for you the individual quadratic Casimirs coming from the two sectors R plus and R minus. And if you consider evolution of a tau A state to a tau A state for a time t, what you also get is you get these two polynomials associated with this composite representation S. This is what I'm associating with, times this precisely this factor, this e to the power n factor. Right. So in conclusion, what this piece of work has done is essentially we have tried to give a geometric prescription and constructed partition functions for 2D angles on various Riemann surface, starting from the droplet picture of unitary matrix quantum mechanics. And it seems that the Hilbert space on the droplet side does contain information of generic 2D angles on Riemann surface. and also its q-deformed analog. Now, what we saw is that the system decomposed into two chiral sectors, and we studied we studied them individually, and then later joined them this in the large and limit, and joined them to get the evolution of the full theory. So again, there were a bunch of dubious steps, you could say, as Paul also pointed out, that we did take, but the catch here is that, you see, the very starting point was this collective field theory, which is something that we recovered only in the large and limit. So now, in order to do our later calculations also, we had to stick to this large and limit, which sometimes may not always be mathematically well defined, but formally one can continue with calculation. Now, the central upshot, even if you have not followed through all the computational details, the central upshot is that there are these certain very specific coherent states that are there hidden in this Hilbert space, which one can use to generate this Yang-Mills disk amplitude, endpoint generic amplitude, all other various kind of observables on generic Riemann surfaces, just by calculating transition amplitude between these sort of coherent states. Now, there is something that I sort of swept under the rug, which is that when we formed these ripples by hitting my vacuum state with a bunch of A daggers and B daggers, we sort of assume that these does not create any folds or any shocks. So to be more precise, you see, these Fermi surfaces that we drew, we sort of were hinging on the fact that my P plus and P minus Fermi surfaces are so well defined that they are single value. So at a single theta point, you have only this intersecting at a single point of. But your ripples might get large enough such that it starts forming shock waves or folds, as has been discussed in the literature. So what happens is that in such cases, for a single value of theta, P plus can be multi-value. So naturally, when you do such integrals and you're integrating over volume of phase space, and you have to be a bit more careful, and you have to do a much more involved analysis in order to understand the dynamics of particular fold states. So this is what has been studied, but not in much details. They had been studied earlier, far back in '95, and recently by Gautam Mandal and Takeshi Morita. And there has been some follow-up works also by Sumit Das more recently. Of course, because I mean, since '98, it had been an era of holography. It would be great to understand what are the gravity duals of these class of matrix model states that we have, these coherent states, and also gravity duals of these fold and shock states. So my central point of this talk was essentially to give you this sort of, and tell you and to convince you that even in the large and limit, the collective field theory of very simple matrix models actually hides a lot of data. And these beautiful dualities that are there between 2D theories like triangles and matrix models can be exploited in order to uncover much more richer structure from this phase space picture. So with these thoughts, I would here is a recap of precisely the algorithm that one needs to follow in order to get to the various observables for 2D Yang-Mills. And yeah, with that, I would like to write up. Thank you.
Okay.
So, if there are any questions,
thank you very much. Yes.
There is a question.
Bal had to leave, I think, was what he just. He has another meeting. There was one other comment you made earlier, which I wanted to clarify. You said that replacing U with U dagger was essentially well, at least very closely related to area preserving diffeomorphisms.
Yes.
That sounds too strong a statement to me. So I wanted to understand a little bit better what you really mean there. Because the gross Witten model, as you said, has that symmetry, whereas I don't think of it as having area preserving diffeomorphisms. As a
So I mean, by okay. So the total phase space area is nothing but this particular area that you see.
Yes.
What I mean is simply what you have here is you simply consider these lengths. This is nothing but P plus minus P minus, or rather I should say P plus plus P minus, because you're simply adding these two and you integrate it over all theta. That's your area. And you have concrete expressions for P plus and P minus, by which, and so what you essentially need is these commutation relations and the equality between the modes, and you will have this. I mean, this simply follows from I would say the expression of the area and the corresponding algebra. So this was in fact derived in an earlier paper by one of the co-authors, where they essentially studied the phase space, and the entire point was that through so these matrix quantum mechanics, you can just think of them, the phase space, as sort of like constant T slices, a bunch of I would say snapshots of at various T times, and throughout one can show that the area, the cross section of this tube that goes through sort of remains fixed.
Okay. Okay, I will have a look at that in more detail. It's just okay. I think I've been asking questions as we go along, so
I hope it was on time.
Yeah, so maybe I will stop the recording at this point. It's okay.